Hello and welcome to the last session of this course. I am Umar Rashid and I work as a PhD student in Indian Institute of Science, Bangalore. So I'm giving the uh, live interaction session every Friday in which I clear the some of the doubts and I try to solve some of the questions that had been asked in the past. Okay. Sorry, I'll be speaking little slow today because I have my throat is not correctly working. So as I already told you that today is the session 12th of our course. Okay. So uh, the name of the course is Advanced uh, Thermodynamics and Electrochemistry. So we are talking nowadays about statistical thermodynamics. As I already told you that statistical thermodynamics is the branch of thermodynamics that is actually bridging the gap between the quantum mechanics and the thermodynamics. Okay, so the thermodynamics deals with uh, uh, so if we talk about the thermodynamics, it deals with microscopic systems. Okay, but if we talk about the quantum mechanics, it tells us about the properties or tells us to predict how to predict the things for microscopic systems. Right, so in between this there is a statistical thermodynamics. I already explained you in the previous lectures which are available on the YouTube, and the information is available on the Google Drive links, that the main thing about the statistical thermodynamics is the partition function. Okay, so the partition function serves same role in statistical thermodynamics uh, uh, as a wave function in quantum mechanics. Okay, so there are a lot of properties that we can derive if we know the partition function of the system. Okay, the partition function of different systems can be evaluated depending upon the constituents of a system. Okay, so I have described so far what is the partition function, what is an ensemble. Okay, then what are different types of the ensemble, like canonical, then we have grand canonical, then we have micro canonical. Okay, then I have told you how the ensemble partition functions are related to the thermodynamical variables. So I have, in the previous lecture I have shown various relations in which these ensemble partition functions can be related to various thermodynamical parameters, we have Helmholtz wave function, Gibbs energy wave function. Similarly, we have enthalpy, entropy. Okay, so this I have described. Now, the most important property that we chemists are interested about is molecular partition function. So that is the topic that we'll be talking about today. Okay, so the today's topic is majorities molecular partition function. Okay, so today we'll see that how we can determine molecular partition function uh, for different molecules, and from that molecular partition function we can actually derive a lot of important parameters, okay, that are related to molecular partition function. Now, as I told you before that molecular partition function is like any partition function. So what is a partition function? It is actually it calculates probability that a system is occupying state I. Okay, so that is the molecular partition function. Okay, so if we have larger the partition function, that means more accessible states are possible. Larger the partition function, it means more accessible states. Okay, so that is the crux of the partition at a particular temperature. Okay, so partition function is written as summation over all the states exponential minus EA by KB. So this is I write Q. Okay, so this is the partition function. Now, if we have for ideal gases, what happens in ideal gases where molecular interactions are zero? So because for ideal gases the molecular interactions are zero, that means energy levels are independent of other molecules surrounding. Okay, so as a result, what we can write is that we can write that partition function of an individual molecule will then be given by Q summation over all the energy status of a given molecule, where EI represents the energy states of a given molecule. Okay, so this is called as molecular partition function. Okay, now if you see the particles of an ideal gas, they could not be considered as distinguishable if they are different from one another, and therefore the unique label could not be assigned to each. So on the contrary, the indistinguishable particles are impossible to assign a unique label, as they are identical to each other. Okay, therefore if we consider indistinguishable particles of an ideal gas from which the partition function of a system can be expressed in terms of a molecular partition function, then the total partition function will be so if I consider indistinguishable gas particles, then total partition function Q will be given by Q raised power n divided by n factorial, whereas n is number of gas molecules. Okay, so this is for those which are indistinguishable. However, if the particles are distinguishable, then the factor n has to go. Okay, now we have something called as we call this as factorization of partition function. Now for a molecule, like a molecular partition function, the partition function can be factorized. Okay, just like in quantum mechanics we have a wave function. So what we do is we can factorize the wave function into two parts, an orbital part and a super part. Similarly, the molecular partition function, it can be factorized into different parts depending upon the degrees of the freedom. Okay, the vibrational, translational, electronic part. Okay, now we can calculate individually these parts of a partition function, considering the structure of a particular and composition of a particular molecule. Once those parts are determined, then we can calculate the thermodynamical properties of the system that we are dealing with, okay, or molecules that we are dealing. So if we see, I wrote as partition function, a molecular partition function is defined as summation over I e raised to the power minus ei by kt. But if there is degeneracy, then what we have to do is we have to add the degeneracy of each level as well. So summation over I gi exponential minus ei by kt. Okay, now we know that E is the energy of the molecule, right? Now this E energy of a molecule is actually it has different contributions, like it has translational, it has it has rotational, it has electronic, and it has vibrational. Okay, so what we can do is we'll write E as translational plus rotational plus vibrational plus electronic. Okay, so therefore each individual level we can also split into. So EI, as I told you, we can write as ET plus ER plus EV plus E is vibrational, this is vibrational electronic. Okay, this is electronic. Okay, and similarly what we can write as the degeneracy of an ith state, it can be the degeneracy in its translational states plus degeneracy in its rotational status plus degeneracy in its vibrational status plus degeneracy in its electronic states. Okay, so these are the where I have shown here that ETR is translational energy, ER is rotational energy, EV is vibrational energy, and E is electronic energy contribution. And G, T, GR, GV, and GER are their respective degeneracy for translational, vibrational, rotational energy states. So, if we put this equation, what we can write is that Q will be given by summation over so we have Q that is given by summation over G translational, then we have G rotational, then we have G vibrational, then we have G electronic energy level, then we have E translation plus E rotation, E vibration, E electronic by KT. Okay, now if we rearrange this, what we will get is we'll get summation over G T. So we have separated the translational part plus summation over rotation part plus summation over vibrational part plus summation over electronic layers. Now if we see here that each individual part, it contains only the parameters corresponding to a particular energy level, either be it rotational, either be it vibrational, or either be it an electronic energy levels. So what we can do is we'll separate the variables and we'll determine that Q total partition function will be equivalent to electronic partition function plus vibrational partition function plus rotational partition function plus translational partition function. Okay, whereas the electronic partition function will be given by summation over all the electronic vibrational states. Okay, e raised power minus e by kt, and we have vibrational given by summation over all the vibrational states. Rotational partition function summation over all the rotational status, and the last is translational partition function, which is the summation over all the translational energy states. Okay, so now we have determined as different factors of molecular partition function. Okay, okay, so now we have all this. Now from here we'll take up, now we'll individually determine how to calculate electronic, vibrational, rotational and the translational partition function. Okay, okay, so first what we'll do is we'll take up the so this factorization is also called, we call it is this is called as a multiplication theorem. Or factorization of partition function. Okay, now we'll go to translational partition function. Okay, now as I showed you before that translational partition function is given by summation over all the translational status g, where okay e raised power minus e I by kt. So this is the partition function. Now we have to determine the value of an ei, that is the translational energy states. Okay, but we know that translational status are non-degenerate. Gi is also equivalent to 1. Okay, it is always, we call it non degeneracy. Okay, so we call it non degeneracy of translational states. Okay, so that means translational state will be given by summation over e minus ei by kt. Okay, now we know that if we write Schrödinger's wave equation, so if we take the Schrödinger's wave equation for a particle in a box problem, right? So majority of us will have solved it already. Okay, so what is E I equivalent to h square by 8m, then nx square by a square plus ny square by b square plus nz square by c square. Okay, so this is the Schrodinger's equation. Schrodinger's equation when the particle is solved for in a one-dimensional bubble. This is the energy, the equation for the energy that we get. Right? Whereas if we say that here nx, ny and nz, they corresponds to quantum numbers along three principal axes, right? Like x, y and z respectively. Okay, so if we put that we what we'll do is we'll use this equation into the our equation of the partition function, and what we'll get is translational partition function qt will be given by summation over exponential minus nx square h square by 8m a square kt, right? Then we have exponential minus ny square h square by 8m b square kt. Similarly, e raised by minus nz square h square by 8mc square kt, right? So what we'll write it as qt will be given by qx, qy, qz. Here the summation is over nx, ny and nz, right? So here what we have, we represent this as qx, qy and qz, where so what we have done is we have factorized the translational partition function into 3. So if we write qx, this is the partition function across the x-axis, which is given by summation over exponential minus nx square h square by 8m a square kt. Okay, so this is the partition function along x-axis. Similarly, we can do the partition function along y-axis and partition function along the z-axis. The increment of the energy between the energy states of translation, these transitional states are very small, right? So the translational partition function, thus instead of writing the summation, what we can do is we can do the evaluate the integral from 0 to the infinity. Okay, it is because the translation partition functions are very close. So what we'll do is we'll replace summation with integration. So what we'll get is qx will be given by integral from 0 to infinite. Here we have 0 to infinite as well. Then we have E, right? Now what we'll do is we'll put L equivalent to h square by 8 m a square kt. Okay, so what we'll get is q x will be given by summation from 0 to infinite e raised to the power minus L, then we have L n x square d n x, right? So what we have done is we have just replaced this part h squared by 8 makx with this part. Okay, so we got this. Now what we can do is, this is actually a standard integral. Okay, from 0 to infinite e raised to the power minus L x square dot d of x is given by 1 by 2 under root pi by L. Okay, so this is the standard integral. That means if we go back to our previous equation, what we'll get is qx will be given by 1 by 2 pi raised to power 1 by 2, right, 8 m a square kt by h square. Everything is 1 by 2. Okay, here you have to see that under root of 8 is 2 root 2. Okay, so qx is given by 2 pi m kt raised to the power 1 by 2 a by h. Okay, so this is the this is along x-axis. Okay, now similarly we can for y-axis we can derive 2 pi m kt 1 by 2, it will be b by h, and for z-axis this will be qy, this will be qz, it will be 2 pi m kt under root c by h. So what we have determined is, we have determined partial function along x-axis, then partial function along y-axis, and the partial function along z-axis. Okay, so now we have partial function along all the three principal axes. Remember, this is the only the translational partial function, because we are considering the translational energy states. Now if we also showed that total partial translational partial function will be qx plus qy plus qz, right? Now if we put substituting qx qy and qz, so what we will get is q total will be given by, sorry, this has to be multiplied by, because I already showed you that the total partial function is just the multiplication of the individual partial function. Once we do the factorization, it will be 2 pi m kt divided by h cube then A, B, C. Okay, so QT will be given by 2 pi m KT or raised to power 3 by 2 by H cube into V. Okay, or we can also write that the translational partition function is given by 2 pi m KT by H square raised to the power 3 by 2 into V. Okay, so this is the trans this is the translational partition function. Okay, a molecular translational molecular partition function. Okay, so this from this equation we can see that m is the mass, whereas k is Boltzmann's constant, T is the temperature, and V is here the volume of the container. Okay, so thus we have derived this equation using the particle in a box problem. So V here is the volume of the container. Okay, so now using this, what we can do is we can write a quick example and we'll show how this can be used to calculate. Now we have an example. Okay, the question is we have to calculate the translational partition function of H2 confined to a 100 centimeter cube vessel at 398 Kelvin. Okay, so now we have this question here. Okay, we have to calculate the partition function of an H2 which is confined to a 100 cubic centimeter vessel at 390. Now everything is given. First, what we have to determine is, let us try to solve the question. Okay, so first thing is, what is mass of H2 molecule, right? So the mass of H2 is 2.016. Then we have to so what I have determined is this is the molar mass of the H2, and I have divided it with Avogadro's number, because Avogadro's number of the particles are in 1 mole of any substance. Okay, so this gives us a value of 3.348 into 10 to the power minus 27 kg. Okay, so we got mass of H2. Now we have another thing called as a volume, which is given as 100 cubic centimeter. We have to convert it into meter, so we have to multiply it with, okay, so we will convert into cubic meter, that is 10 to the power minus 4 meter cube. Then we have the value of the Boltzmann's constant, which is 1.381 into 10 to the power minus 27 joule per Kelvin. Similarly, we have value of an H, which is 6.626 into 10 to the power minus 34 joule second. Okay, so the translational partition function for H2 will be given by, we'll use the above equation that we have, 2 pi m k t by h square 4 raised to power 3 by 2 dot v. Okay, so we substitute the values. Okay, 2 multiplied by value of m pi 3.14 multiplied by 3.348 into 10 to the power minus 27, then value of k, then absolute temperature, okay, divided by 6.626 into 10 to the power minus 34 whole square, and this thing is whole 3 by 2, and then we have volume, that is 10 to the power minus 4. Okay, so the QT for hydrogen is 1.97 into 10 to the power 20 raised to the power 3 by 2 10 to the power minus 4. Okay, so our QT for hydrogen will be given by 2.769 into 10 to the power 26. Okay, that means about 10 to the power 26 quantum states are accessible thermally for H2 even at room temperature. Okay, so this is how we can calculate the partition function. This was the translational partition function. Now I'll be going more about sort of okay, so this is the translational partition function. Okay, so the value of the translational partition function can be very huge even at very low temperature. Why? Because the translational partition functions are very close to each other, levels are very close to each other, so even at very low temperatures a large number of the levels can be occupied. Now next what we have is we'll go to rotational partition function. Okay, so here we have to consider the rotational energy level. Just 1 minute. For rotational energy status, we have considered that for diatomic molecule, the jth state energy is given by okay. So this is if we consider a diatomic molecule, and we get the energy for a rigid rotor as this, right? So now, whereas j plus 1 is the these are the transitions, this is the this is the degeneracy of the jth state. Now here we have I, right? I is called moment of inertia. This is moment of inertia of the diatomic molecule. J is rotational quantum number, and its value can be 0, 1, 2, 3, etc. Okay. And sorry, this is not this jj plus 1 is actually in the energy itself. Okay. The degeneracy is given by sorry, degeneracy of jth state is given by 2j plus 1. Okay, so that means e j is given by 2j plus 1. It will be gj. Okay. Therefore our rotational partition function will be given by q r. We can write as, here we'll write as gr summation over all the j So I have just substituted the value of ER and GR from our previous equations. Okay. Now if we say that the rotational levels are sufficiently closed spaced, okay, so they are not that far as compared to our vibrational levels or as compared to the electronic energy levels. Okay, so they are little bit closer to each other, hence they can be taken as a continuum. Okay, so what it allows us to do is it allows us to change integration, summation to integration. So q r will be given by okay after integration, or we can write that as okay. So what we have do is we have substituted alpha, which is given by h square by 8 pi square I k t. Okay, now what we'll do is we'll again put z equivalent to j plus 1, then delta z will be given by 2j plus 1 into dj. So then if what we'll get above equation as qr will be given by summation from 0 to integration change from 0 to infinite exponential minus z alpha dz, which is given by 1 by alpha, which is standard variable. So if we put that value, qt will be given by 8 pi square I kt by h square. This is our rotational partition function. Okay, this equation is only true for homonuclear diatomic molecules, like heteronuclear diatomic molecules like NO, HCl, etc. But in case of a homonuclear diatomic molecules, so this is for heteronuclear diatomic molecules. Okay, for homonuclear ones, what we have to do is we have to divide it only the half of the rotational terms will be present. So how we do that is we divide it by a factor called as a symmetry number. I have explained a little bit about the symmetry number in my previous lectures. Okay, so the rotational partition function for any linear molecule will be given by this. Okay, so symmetry number, what it does is it tells into it takes into consideration that when we have a homonuclear molecule, then the two states in which nuclear A or nuclear B can be on the either side, they are actually the same configuration. So it neglects one of them and takes one into consideration. Okay, so this is a general equation for rotational partition function of a linear or homo or heterodiatomic molecule. For the value of an alpha for homodiatomic symmetrical linear molecule is 2, because end-to-end rotation yields an equivalent orientation. On the other hand, the value of an heteronuclear asymmetric linear molecule like carbon dioxide or SCO is always 1. Okay, now we have derived this equation. Okay, now what we'll do is we'll do an example. We'll calculate how we can calculate the rotational energy state. So the question is, calculate the rotational partition function for H2 at 300 Kelvin moment of inertia for H2 is 4.59 So now we have to calculate the rotational partition function for an H2 at 300 Kelvin, whereas the moment of inertia for the hydrogen is given and the symmetry number given is 2. Okay, so we'll directly go to the solution. Okay, so we know that what is the rotational partition function equivalent to 8 pi square I kt by sigma h square, right? So q r will be given by 8 okay, so the value it will be, this is the rotational partition function for hydrogen at 300 Kelvin. So what it tells us about is at 0 Kelvin, at room temperature, only hydrogen thermally accessible rotational states for hydrogen is only 1 to 2 maximum, but the number of transitional states that are available for thermally accessible for hydrogen at room temperature is 10 to the power, as I have we have derived previously, 10 to the power 26. So this tells us that the rotational energy levels are very highly spaced as well, and they are less accessible at a particular temperature than transitional states. That is expected on the basis of states that we are talking about, rotational states and vibrational states. Okay, So we have covered the translational, we have converted the rotational. Now we'll go to vibrational partition function. Okay. Okay. So as we have shown here, the vibrational partition function will be given by QV. It will be given by summation over all the vibration states. Okay, summation over V e raised to power minus EV by KT, right? However, GV is always 1 because the vibration states are not degenerate. So what we are left with is QV is given by summation over V e raised to power minus EV by KT, right? Now what we'll use is we'll use from if we recall the harmonic oscillator problem, we know that EV is given by V plus 1 by 2 H nu, right? Where nu is actually the fundamental frequency and V is vibrational quantum number, which can change from 0, 1, 2, 3, etc., right? So if we determine V is equal to 0, it will be 1 by 2 H nu. So this is our first state. When vibrational quantum number is equivalent to 0, our energy will be equivalent to 1 by 2 H nu. This is also called as a 0 point energy. Okay. Now if we go towards this expression, this vibrational state, this quantum partition function, wave function state, so here the energy status EV, they refer to the energy of the vibration states which is in excess to the ground state energy. Okay, in the present case, the ground state energy which corresponds to V is equal to 0 is not 0, but it is actually 1 by 2 H nu. Therefore the expression for energy appearing in the partition function will be EV, sorry, I'll write it, will be EV will be given by V plus 1 by 2 H nu, but we have to subtract the ground state energy, that is H nu, so that is equivalent to V H nu. Okay, so QV will be equivalent to summation over E minus V H nu by KT. Okay, now if we want to simplify the equation, what we'll do is we'll put X equivalent to H nu by KT. Okay, so QV will be given by exponent summation e raised power minus V of X. Now the vibrational energy status, they are not closely spaced, therefore here we cannot replace the summation with the integral, but we can take values like 0 1 2 3 4. Okay, so QV will be given by 1 raised power 0 plus e raised power minus x, right, plus e raised power minus 2x plus e raised power minus 3x, like this. Okay, so that is QV will be given by 1 plus e raised power minus x plus e raised power minus 2x plus e raised power minus 3x, etc. That is given by QV is given by 1 plus e raised power minus x raised to power 1 plus e raised power minus x raised to power 2, right? So this is a series. Called as geometric series, right? With common ratio of e raised power minus x, so therefore QV will be given by 1 by 1 minus exponential minus x, right? That is given by 1 divided by 1 minus, put the value of x, minus h nu by kt, or we can write QV is given by 1 minus this is our vibrational state. So this is our vibrational quantum or vibrational state. Okay, so what it tells us is that we have calculated all the states till now, vibrational, rotational, as well as translational. Give me 2 minutes, I'll just So this completes our uh, vibrational quantum number. Okay, now we have another the last one, vibrational partition function. Now we have last one called as rotational partition function, sorry, electronic partition function. So we have electronic partition function. Now for electronic partition function, if we say that many monatomic substances as well as fewer polyatomic molecules, they possess multiple electronic ground states. Okay, so in most of these cases, in their nominal state, there are two or more different electronic levels where the energies are so close that they may be assigned a single energy level with a statistical weight factor of greater than unity. In addition to such levels, there may be excited electronic states whose energy may be greater than that of the ground states. As we increase in the temperature, more excited states can become occupied. In such cases, the electronic partition function is greater than unity and varies with the temperature. The electronic partition function is given by QE is given by summation over GE, where GE is the uh, degeneracy of the electronic energy level. So at majority of the temperatures, the value of the QE is almost to 1 because only the first ground state is occupied. But for other molecules or systems, there can be more levels occupied. Degeneracy can be more than 1. So as a result, it goes above more than 1. Whereas here the G represents the statistical weight factor of the electronic level, normal or excited, and is equivalent to 2j plus 1, where j is the total angular momentum number in a given state. Okay, ec is the energy of the electronic state in excess to the lowest energy. Thus, if we say we can say that that as majority of the times only the ground state is occupied, therefore what we can represent QE at majority of the times is equivalent to the degeneracy of the ground state. Okay, so degeneracy of the ground state is G0, so thus that is the electronic partition function. However, for all the substates, it's not, it can be something else as well. Okay, but if we consider that degeneracy as 2j plus 1, whereas j is total angular momentum quantum number, right? Then QE will be given by summation over 2j plus 1 e raised power minus EE by KT. But in general state, the energy EC is 0, right? So our equation will go to summation over 2j plus 1, that is directly equivalent to e raised power 0, that is summation of 2j plus 1. So this tells us that the contribution of any state to the electronic partition function is majority of the times 2j plus 1, the degeneracy of the ground state or degeneracy of the ground state. Now we have to now consider the what is the ground state electronic degeneracy. Okay, because that is the only thing that is majority of the time is contributing to the electronic partition function. Okay, so that is coming around. What is the ground state electronic degeneracy? For example, if I will write for simple atoms, for example, we have an atom, right? So we have an H, hydrogen, then we have helium, then we have sodium, and then we have calcium. Okay, okay, so we'll write their term symbol. Okay, okay, so what I have done here is I have written the various atoms, and I have written the ground state term symbol corresponds to a particular electronic state, and therefore the degeneracy, as I have told you, is given by 2j plus 1. Okay, so the j is here 1 by 2, so degeneracy is 2. Similarly, here 1, here 2, here 1. Okay, okay, so we had determined the ground state electronic degeneracy. Now this term that I have shown here, like L, J, this I have explained little bit in my previous lectures, is actually shorthand notation. So what this term, I told you that it is called as a Millikan term symbol, and it tells us it's a shorthand notation to represent the angular momentum of any state. Okay, so any atomic state, we can represent the angular momentum. All the angular moments are actually represented by this term, be it a supine angular momentum S, orbital angular momentum L, or the total angular momentum J. Okay, so mathematically, if we say that the total supine angular momentum is the vector summation of individual supines. Similarly, for orbital angular momentum is total summation of individual orbital angular momentums, and the total angular momentum is L plus S. So now this is only for those atoms whose atomic number is less than 30, because for higher uh, 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 atomic number elements, the supine and angular momentums are so interacting to each other that we have a JJ coupling. So supine and orbital angular momentum interact first, and then the individual angular momentums interact. Okay, so this is called as a Russell-Sanders coupling or JJ coupling that I have explained previously. Okay, so what I have explained today you is we have we have explained the partition function. How why is the molecular partition function important? Because from the molecular partition function, if you see, we can determine a number of the parameters, right? So we can determine a number of parameters. Number of parameters means uh, we can predict different molecular properties. Okay, so for what I have done is I have told briefly about the partition function, then the molecular partition function, and then how the partition function can be factorized into different components like rotational, vibrational, and vibrational partition function, electronic partition function, how we can calculate different partition functions. Okay, and the electronic partition functions. Okay, so this completes our discussion on the majority on the partial functions. Okay, now what we'll do is we'll try to solve more questions because still we have some time. Okay, so okay, so now we'll try to solve some of the questions that we have. Okay, so for that I'll just give me a second. Okay, so now we'll try to solve some of the questions. The first question that we have is for a non-linear system, the potential energy in absence of external force is a function of. Okay, so we have a non-linear system and we have to find the potential energy as a function of. Okay, so okay, so see, for a molecule, we have 3n variables. Okay, out of them 3 variables are for translation, three for rotation. Okay, since total is 3, so variables for potential energy will be 3n minus 3 plus 3, that is equivalent to 3n minus 6. Okay, so that solves our question. Okay, now we have second, which of the following statement is correct for an activated complex? Okay, uh, it is the highest point along the maximum energy path separating the reactants from the products. Okay, it is the lowest point, it is the highest point along the minimum energy path separating the reactants and the products. So this is the activated complex. Activated complex is like the third is the correct answer. It is if I show you a potential energy surface, right? So for example, if we have an energy as a function of we have potential energy as a function of reaction coordinate, and this is our reactants changing to products. So for example, this is A plus B and this is X plus Y. So what will happen is here you will have an activated complex A plus B. Okay, so this is called as an activated complex. This is reaction coordinate and this is energy, right? So the highest point, but it has to be the lowest energy path. So this is our activated complex, so the correct answer is 3. Okay, now the cross sectional area of CH2 CH3 and H2 are 2 into 10 to the power minus 9 meter and this respectively. Using the collision theory, calculate Bmax. Now we have to use the collision theory to calculate Bmax. Okay, so that we can do. Okay, we know that area is pi r square, right? So meter square, so r CH3 will be given by so the radius of CH3 is given by 2.5 into 10 to the power minus 10 meters, right? Similarly, we can determine radius of H2. So radius of cross section of H2 is given 1.5 10 to the power minus 19 meter square, right? So radius of H2 will be given by 15 by pi 1 by 2 into 10 to the power minus 10 meter, that is given by 2.18 into 10 to the power minus 10 meter. Therefore, B max as per collision theory will be given by cross section area of CH3 plus cross section area of H2. Right, so that is given by 2.50 plus 2.18 into 10 to the power minus 10 meter. That is given by 4.68 so that solves our question. So what we have done is as the cross section was given, so we have substituted using the cross section we have determined the radius of H2 and radius of CH2. From that we can calculate the Vmax as per the collision theory. Okay, now consider the reaction CH3 plus H2 is equal to CH plus 4. Calculate the average velocity of reactant molecules at 300 Kelvin temperature. We have to calculate the average velocity, right? So this is the expression from the for the average velocity from the Maxwell-Boltzmann distribution. If we substitute the values, okay, so the value will be given by So I substituted all the values. What we get is it will be 1900 meter per second. I'll show you what I have done is I have used the expression for the average velocity. Now I know the average velocity expression 8 by pi kt by mu under root. Okay, so I have to calculate the reduced mass. Now the reduced mass of CH3 and H2 can be calculated from their mass, but it is a mass of 1 mole of the substrate. So what we had to do, we had to divide it by Avogadro's number to get for 1 pair of molecule. Now once I got there, we can calculate the average velocity. Okay, so that completes our question number 4. Okay, now we have question number 5. Use the obtained in question 3 and question 4 and calculate the value of a use the obtained values question 3 and question 4 and calculate the value of steric factor, given that the pre-exponential factor is 5 into 10 to the power 12 centimeter cube mole inverse second inverse. Okay, so what we have to do is we have to use the values that we have determined in our previous questions and use them to calculate the pre-exponential factor, right? We have to calculate the steric factor. Okay, so what we'll do is, yeah, okay, so what we'll do is we'll first see the steric factor. Expression for the steric factor is given by A is equivalent to rho B max square into VR, right, where A is the exponential factor, P is steric factor, right? So P will be given by A by pi B max square VR. So P will be given by 5 into 10 to the power 12 centimeter cube mole inverse second inverse into 10 to the power minus 6 meter cube per centimeter cube divided by pi B square max into VR, that we have determined in our previous. So pi multiplied by B square max will be given by, sorry, 1 minute, this is running a little slow, so I just 3.14 value of the pi, value of B max will be 4.68 into 10 to the power minus 10 meter. This is square 6.88. Okay, so this is the value of pi bx square. Okay, now put that if we put those values, P is given by 5 into 10 to the power 6 meter cube per mole per second by 6.88 into 10 to the power minus 90 meter square per molecule into 1900 meter per second into 6.023 into 10 to the power 23 molecules per mole, right? So we can do is, see, we have here molecule, right? This molecule and this molecule will go, right? Then we have meter cube, this meter square and this meter will go, right? Then we have this second and this per second will go, this mole and this mole will go. Okay, so what we are left with is P will be given by 63.54 into 10 to the power minus 4. That means P is given by 6.354 into 10 to the power minus 3. So we have calculated the factor correctly. Like majority of the questions are getting removed automatically, but that's okay. Okay, so now what we have is okay, which of the following statements is correct for a reaction to take place? For early barrier reactant, should a vibrational energy more than the translational? For early barrier reactant, should be translational more than the vibration? For late barrier, should translational energy more than vibrational? The correct answer is actually B, 2. Okay, for early barrier reaction, reactant should have a translational energy which is more than the vibrational. Okay, then we have question 6. Question 7, which of the following statement is correct? Here the correct statement is actually 1. For late barrier reactant should have a vibrational energy more than the translational. Then which of the following is the correct expression for 0 point vibrational energy? So we have to see 0 point Why this is called a 0 point vibrational energy is because it is the only energy that is available for a system even at 0 Kelvin. Okay, that is the reason it's called as a 0 point energy. Okay, so if we see the Morse potential curves, right, or any graph like we see like this, right, and then we see the states. So basically this lowest state is corresponds to 0 point energy. Okay, so we know that vibrational energy is given by V plus 1 by 2 h nu. So 0 point energy is when V corresponds to 0, that is 1 by 2 h nu. Okay, so the value is 1 by 2 h nu, where nu is fundamental frequency. That frequency we can actually derive as if we have used like V is equal to 1 by 2 h 1 by 2 by k mu. Okay, so we can determine this fundamental frequency from for any bond depending upon we know the atoms that it is formed in between and what is the strength of a bond. Okay, so 0 point vibrational energy. So the form of a 0 point vibrational energy uh, that I have shown 1 by 2 h nu. Okay, next we have the vibrational degrees of freedom for pyridine R. Okay, so for pyridine vibrational degrees of freedom, so I'll make the structure of pyridine. This is the pyridine. Okay, so it is C5 H5 N, right? Total number of N is 11. 3N will be 33. Now we know that sinus therefore vibrational degrees of freedom for the pyridine will be 3n minus 6 because it's a non-linear molecule, so it will be how much? 27. Okay, so for if it's a linear molecule like carbon, just like, okay, let's take carbon dioxide. So carbon dioxide has structure of C double bond O, and similarly we can take water molecule. Okay, so here N for both is 3, for N is 3, 3N will be 9, 3N will be 9. But if you see for carbon dioxide, it will be 3N minus 5, the vibrational degrees of freedom. But for this it will be 3N minus 6, so here it will be 3, here it will be 4. Okay, so this is the degrees of the freedom. Depending upon the degrees of the freedom, we can have a number of the fundamental modes. So more degrees of the freedom, more number of the fundamental modes that we have. Which of the following partial function depends on volume? Rotation, translational, vibration, or now partial. I have shown you, actually we can have a revisit about this.
Okay, so if we go towards the translational partition function that I have shown, so this is the translational partition function. Yes, as as you have seen, it depends upon the volume, so the translation function depends upon the volume. Okay, so this completes our this today's topic, and also it completes our course. So briefly I will try to go through the things that I have taught today. Okay, so the first thing that I taught to today is the statistical thermodynamics. So as the thermodynamics is applicable to the microscopic systems, macroscopic systems, the quantum mechanics is applicable to microscopic systems. So statistical thermodynamics is something that bridges a gap between the quantum and thermodynamics. Okay, just like we have a wave function in quantum mechanics, similarly we have a partition function in quantum this statistical mechanics. The partition function we can derive various thermodynamic parameters of a system. So in my previous lectures I have shown you the relation between the quantum mechanics and what are the different kinds of the ensembles, and what is the significance of ensembles, why do you use ensembles. Okay, then I have shown you what is a molecular partition function, and for a gases what is a molecular partition function, because for ideal gases, because the gases are not interacting with one another, so the individual energy levels, they keep their identity, whether it's a molecule that's stand alone or whether it's a mixture, right? So as a result we can take the summation, okay. So then the expression for the partial function is summation over all the partial functions, over all the energy levels, and the expression is shown here. Okay, for those molecules which are indistinguishable, we have to divide by a factor of n factorial. Okay, then I have shown how the partial function can be factorized, just like we factorize the wave function. We can similarly factorize the partial function. We factorize the wave function into various orbital part and the super part. Similarly we can factorize the partial function and into various contributions, like translational partial functions, rotational partial functions, vibrational partial functions, and electronic partial functions. So the total partial function is just the multiplication of uh, the total partial function is just sorry, here it is multiplication of okay. It is multiplication of the individual partial functions. Okay, so this is called as a factorization theorem. Okay, so from the factorization we can have our electronic part, vibrational, rotational, and the translational part. So we have taken first the translational part, and we have used the particle in a three-dimensional box to derive the expression for the translational partial function. We have used it, and then what we got into the equation is we have made approximation that since the translational energy levels are very continuous, so we have replaced the summation by the integration, right? So what it allowed us to convert it into a standard integral. Then similarly, then so the expression that we got is 2 pi m kt by h square dot v, where v is the volume in which our gas molecule is confined to. So the translation partial function depends upon the mass, depends upon the temperature, and depends upon the volume. As an example, we have calculated the partial function for hydrogen, that's confined to 100 cubic centimeter and 398 Kelvin, and to our surprise the value of the partial function came to be 10 to the power 26. That means 10 to the power 26 translational states are accessible for a hydrogen molecule even at a room temperature. Okay, then we have shifted to the rotational partial function, where what we have used is we have used instead of using we have used a two-dimensional rotor quantum equation to derive the rotational partition function. Now solving this integration and again approximating that the rotational energies are uh, fairly closer to each other as compared to vibrational status, so we have replaced the summation by the integral. So replacing summation by the integral, we have determined the equation for heteroatomic molecules, that is pi 8 pi square I kt by h square. So rotational partition function depends upon where I is moment of inertia, t is temperature, and h squared. Okay, but for nuclear ones, what we have to do is we have to divide it with the symmetry number. It's because the two rotational two states are actually indistinguishable from one another. Okay, then we have I have also explained the vibrational partition function, and also I have also explained the rotation electronic partition function. So the vibrational partition function is just the summation over the status, where we do not use the integration approximation, and the electronic partition function is majority of the time is equivalent to that of our or that of the degeneracy of the ground state. The degeneracy of the ground state can be directly derived from the Millikan term symbols. Okay, so the Millikan term symbol will tell us the total value of the J, total angular momentum quantum number. The total angular momentum quantum number tells the degeneracy of the ground state. So if we know the degeneracy of the ground state, and majority of the temperatures only the ground state is accessible at the room temperature. Okay, so as a result the partition function is equivalent to that of the degeneracy of the ground state. But if the higher electronic states are accessible at the room temperature for some molecules, then those states have also to be considered. Okay, so this is the yeah, this is the partition partition function. Okay, so this was so today was the 12th session of our NPTEL course. Okay, so today is the last one. I wish you all the best for your exams, and if you have any confusion, I think probably you will be able to request, or you can comment on the YouTube. I'll be able to answer the questions as well. That's not an issue. Okay. Okay, so this completes our course. I thank you all for opting this course, and for listening to me. So today I was little my health was not good, so I was not able to speak properly. Thank you for being with me, and anyways the lectures and everything will be available on the YouTube and the Google Drives. You can access it anytime. Thank you so much. Thank you.